talk a little bit about the role of a dielectric and a capacitor. So we're going to start off with an air gap capacitor. So I have some battery, and the battery is going to have a positive charge on one plate of the capacitor and an equal and opposite negative charge on the other plate. We'll call this charge Q0, and on the negative plate minus Q0. So capacitors are not creating charge out of nothing. Whatever charge there is on the positive plate, you always have opposite that on the negative plate. So the total charge of the capacitor is going to be 0. If we call the space between the two plates D, we can calculate what the electric field is going to be between those two plates. So it's going to be the potential difference between the plates that's caused by the battery divided by that separation. Now, if this value of the electric field is too large, then the air in the gap between the plates will break down. You have a conducting path, and the negative charges will just jump over and short out the positive charge. So the material that makes up the space between the two plates is limiting what value the electric field can be in the capacitor. That therefore limits how much charge can be placed on the capacitor, because we know for a capacitor that the charge is proportional to the voltage. All right. So one thing we can do is put a material in between the plates of the capacitor that can be polarized. So we put a slab of a polarizable material, which is called a dielectric, in between, but not touching, so you don't have a conducting path. And the molecules that make up this dielectric in the space in between are going to rearrange themselves, rotate, if you will. The molecules will rotate around so that you have a net positive surface charge on the part of the dielectric that's closest to the negative plate. And a negative surface charge at the end of the dielectric slab that's closest to the positive plate. And that's just the effect of the polarization of this dielectric material. So what has that done for us, having like some plastic or some other material in between the plates of the capacitor that can be polarized? Well, that polarization has reduced the electric field in the capacitor. Reducing the electric field but keeping the voltage fixed from the battery means that you're able to store additional charge on the capacitor. That means you'll actually store more energy in the capacitor by having the polarizable material in between the plates of the capacitor. All right. The way we talk about the effect of this dielectric, we will have an electric field in the presence of the dielectric, and we have an electric field when there's nothing there. And we'll make a ratio called kappa, which is our original electric field divided by the electric field that is present when this dielectric is here. So that is a reduced electric field. And the more polarizable this material is, the more that the electric field is reduced. And that is called the dielectric constant. And every material would have some value for its dielectric constant. You can see it's a dimensionless quantity because it's a ratio of two electric fields. Kappa is going to be bigger than or equal to 1 because E is going to be smaller than or equal to E naught. And then the other instance where you might see this is in terms of the permittivity. So in a material that could be polarized, the permittivity is going to be kappa times bigger than the permittivity of free space, epsilon naught. And epsilon naught was our 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared.